Alright guys, today we're going to start volcanoes. And I will be back soon and I miss you all, but I still have got to teach you. So, volcanoes. This map should look familiar. You did a worksheet on this where you had to cut out the pieces, put them together, and you should have seen that over here, this is called the Ring of Fire. I believe you might have had earthquakes and volcanoes, and for right now we're just looking at the volcanoes. And they follow along plate boundaries. So it shouldn't be a surprise that volcanoes usually occur on some type of boundary. So volcanism is all the processes that are associated with the discharge of magma, hot fluids, and gases. Now when we say hot fluids, we mean magma itself, hot water, anything that can be considered a fluid. Gases, you can get carbon dioxide, you can get methane, you can get a whole bunch of stuff. You can get some really nasty stuff as well. And it happens at convergent boundaries, divergent boundaries, something called hot spots, and there's also a type of volcanism known as flood basalts. Now, when I say that it happens at convergent boundaries, any volcano that occurs at a convergent boundary is said to be convergent volcanism. So, this picture should not be new to you. This is a convergent boundary. And so, we spent a lot of time talking about this section here. Whenever we reach about 100 kilometers in depth, melting takes place, chemical reactions occur, and the material being less dense rises to the top and we have a volcano. Now because this is oceanic versus continental crust, we have a continental volcanic arc. And that was something that we went over in the tectonics unit. But as I keep saying, everything in our class is connected, and here we go. So in convergent volcanism, there is different types of tectonic activity that can make it occur, as long as it's at a convergent boundary. So an oceanic continental subduction zone, like we have in the picture, here the denser oceanic plate slides under the less dense continental plate. Remember, the older, colder, denser plate goes underneath. And parts of the plate melt and magma rises to form a volcano. Once again, what we've been talking about over here. These are explosive. They're not going to be gentle. Then, at divergent boundaries, we also have volcanism, but this is non-explosive. Here we have two plates spreading apart. This should look very familiar, mid-ocean ridge. We have the plates spreading apart. At divergent boundaries, you're going to get what we call pillow basalts. So, pillow lava, it is basaltic in nature, but pillow lava meaning that these blobs look like pillows. Not comfortable, but as far as looking at something and trying to make sense of it, sure, pillow lava. But they're going to be basaltic rock. Then we get something called hot spots. And something I want you to pay attention to is this guy over here. Hawaii is a hot spot. An unusually hot region of the Earth's mantle where high temperature plumes of magma rise to the surface. So thinking about that and looking at this picture, zoom in a little bit here, this would be your hot spot, your unusually high temperature and plume of magma. So what's happening is this plume is continually bringing magma to the surface, becoming lava, and it's piling on top of each other to create the islands. Now in the next slide, you're going to see this a little bit more clearly. The plate is moving in this direction of the arrow. So as plate tectonics continues to occur, This lithospheric plate is moving in this direction. We're going to call that a northwest direction. So the plume, the hot spot, stays in one location, but the plate continually moves in this direction. So if you take a look at the ages, over here is the oldest island, 3.8 to 5.6 million years. And over here, we have 0.7 million years to present, really, because it's continually getting larger. Now, if we wait millions and millions of years, Hawaii might be over here, and we might have a new island called Bosch Island. Who knows? But what the important thing is that the hot spot does not move. It's the plate that continues to move. Take a second to read this. It should make sense that the inactive volcanoes are the ones that are no longer above the hot spot. You have to be on top of the hot spot in order for you to be active. The hot spot is the plume that provides the magma for that volcano. So if you're not on top of the hot spot, you're not active anymore. I would like you to take a few minutes, and I'll give you about 2 minutes or so, to write down your response. How can hot spots help us? What do you think hot spots can tell us as far as earth science and geology goes? You should be jotting down an answer somewhere on a scratch piece of paper or the paper in front of you. Okay, that wasn't quite 2 minutes, but I can't stand waiting here in my office, so hopefully you have something written down. Let's take a look if you have the same thing I have. Chains of volcanoes that form over stationary hotspots, they give us information about the motion of the plates. So depending upon how fast the plate is moving, you can look at the development of islands. So the rate and direction of plate motion can be calculated from positions of the islands or volcanoes if you take a look at Hawaii. Then we get to something called flood basalts, and we had this mentioned to us whenever we looked at the video about dinosaur extinction. But flood basalts form when lava flows out of fissures. And a fissure is just a ginormous crack in the earth. And over time, what you'll get is something called a plateau. And here's a picture of one. So if you just take a look at what it says for the figure, and I'll zoom in so you can read it too. Huge amounts of lava erupting from fissures accumulate on the surface, often forming layers a kilometer thick. Over time, streams and other geologic forces erode the layers of basalt, leaving plateaus like this one. So basically, what you have, all this material right here was gushing out of a fissure and formed this outcrop, and over time the stream wore it down. So what you get left with is a plateau. Now, there are different factors that affect volcanic activity: pressure, temperature, and magma composition. Now, when we say composition, we want to know, what is it made out of? So, dissolved gases. The more gas, the more explosive. Think about a 2 liter of pop. If it's been sitting on the shelf for 10 years, some of that gas escaped. So when you open it, you might not hear the s of the bubbles leaking out. Or even if you shake it, maybe you only get a little bit of fizz. Whereas if I have a fresh bottle of pop, if I shake it up, it's going to explode when I open it. So the types of gases that are in the lava or the magma are water vapor, carbon dioxide, hydrogen sulfide, and sulfur dioxide. That stuff can get pretty yucky. Then we have viscosity. We talked about this just briefly before I was out, but remember that viscosity is the resistance to flow. So the higher the viscosity, the stickier it is, the harder it is for it to go downhill. Think about pouring water on a ramp. Water is going to go very, very quickly, whereas something like molasses or corn syrup is going to be very, very slow. Temperature and silica content also help with viscosity. Higher the temperature, the less viscous it's going to be, and the higher the silica, the more viscous it's going to be. And you'll have a couple of notes on that. For viscosity, high silica means more sticky. Think of corn syrup. I could actually take a pipette and put air bubbles into the corn syrup. Whereas if I had water, if I squirted air into it, the bubbles would just come to the top. So if it's trapping gas, it's going to be more explosive because that gas wants to escape. Low silica means it can run. It's not as viscous, so it's going to be a gentle flow, not explosive, because that gas can escape. Okay, so types of magma. We have basaltic, andesitic, and rhyolitic. These are the three main types. Basaltic, has less than 50% silica. That means that it's lower. Gases escape easily, and we have gentle eruptions. Basaltic magma is going to give you basalt or basalt-like rocks. Andesitic is in the middle, 50 to 60% silica. You're going to find this at oceanic continental subduction zones. And then there's rhyolitic. Rhyolitic is very sticky. It has lots of silica in it. That means it's very viscous. And these are not going to have gentle eruptions. These are going to have explosive eruptions because large amounts of gas gets trapped. So if gas is under pressure, it wants to escape. Here, gas is trapped. The pressure increases, and you get an explosive eruption. So I really like this picture because it shows you where different types of eruptions are going to occur. So here we have quiet eruptions. The most active volcanoes are associated with hot spots under oceanic crust. So here we have a hot spot. Think of Hawaii. These are basaltic lavas. They flow very easily. They're not going to be gentle. Think of it like a steady stream of lava. Here at a divergent boundary, notice the mid-ocean ridge, we're going to have underwater eruptions where we get the pillow lava. And they are going to kind of just come out at the divergent plate boundary. And this is your pillow basalt. Then over here where we have oceanic continental, we're going to get your explosive dangerous eruptions. This image is actually from your book. I'm going to zoom in up to the top, figure 18.11, so that means chapter 18, figure 11. And so here we have your basaltic lava. See how it kind of just oozes out there? Not explosive. Then we have your andesitic lava. It's intermediate. It is explosive, but if you look in the picture, there's also some flow to it. So yeah, over here, we do have maybe some eruption going on, but it's also flowing as well. And then at the bottom, we have rhyolitic, high viscosity, and it's very explosive. It's hard to see in this picture, but imagine all this just being cinders. And whenever a gas bubble comes to the top and erupts, these tiny little cinders, like what they put in snow whenever it's really bad out, they just spew everywhere. And then we're going to get into some different types of volcanoes, but here's a few pictures. I found some cute clip art that showed different types of volcanoes. And then over here we have an actual real picture of a volcano. So composite. Composite volcanoes is your classic type of volcano. Whenever you think of volcano, you think of this shape. So it's a cone shape, steep, smooth, and it usually has just a single plume of smoke emitted from a vent. And it has alternating layers of pyroclastic material and lava flows. Mount Augustine is what is in this picture here. And here we have a diagram where you have your single vents, and then over here you can see the pyroclastic material, which is like chunks of rock and little cinders that are covered with lava flows. So basically you get pyroclastic material, lava flow, pyroclastic material, lava flow, pyroclastic lava, pyro lava, so on and so forth. Now a shield volcano, they're the gentle giants. It has long, gentle slopes. They are not steep at all. Basically, you just have lava, fluid lava that continually piles up on top of each other over and over. It's more like a dome than a cone, and they're called shields because they look like as if you were to take an ancient shield and lay it on its side. And then we have Mauna Loa is the biggest volcano in the world, and it's about 5.5 miles high, but 3 miles of that are underwater. Here's a picture. Now you can see that it kind of just gently goes like that. Think of a shield being laid down, and that's kind of the shape you would get. Then we have a cinder cone, and it's like a cone, but think of it much, much smaller than what a composite would be. And all it's made out of are little cinders or ejecta called tephra, but think of little pieces of cinder. Now if you're going to Pitt or CMU and you're on your way there, on your right hand side is basically like a gravel yard, and think about the piles of gravel. They're not very tall, but they're steep. And that deals with the physics of the cinders, but we'll get to that later. Anyway, they're going to be less than 500 meters tall. Obviously, the piles that you're going to pass going to Pitt aren't made of the same thing, but I just wanted you to get that shape in your head. And a lot of the time, they'll actually form near other volcanoes, but they're much smaller. And here's a picture of one. Now, here are some parts of a volcano, and I actually want you to pay attention to this picture because you will need to know the parts. I'm going to circle that. It's in chapter 18, but you have the magma chamber, a crater, which is where the top is. You have a vent in a conduit, a caldera. Now, calderas are volcanic craters that form when the summit or the side of a volcano collapses into the magma chamber that once fueled the volcano. So, let's say that this magma chamber empties out completely. What can happen is this top part can fall down into it, and you would get a caldera. Here we have one that has actually turned into a lake because it filled with water. If you want to see more pictures of volcanoes, you can go on to my website. This PowerPoint is on my website, and you can click on the link and it will show you different pictures and diagrams. You will be getting a diagram of a volcano, but this is it for today. So I hope you all have an awesome possum day, and I can't wait to see you guys soon. See ya!